Okay, I'm going to go ahead and start. This is topic is on probability and statistics, and it is for both K through 6 students that you'll see some problems for, and a little bit more challenging problems for teachers. And let's go ahead and get started. So I put the resources up here that I'm using with the web links, which are some virtual dice rolling programs, 2 of them, and then coin flipping program, spinners, and a Monty Hall simulation. So let's go ahead and do this. Now, one thing you can do to make learning stats and probability interesting for your students is maybe tie it into games that you can do right in the classroom. For example, I've seen people do the thing where they have paper wadded up in a ball and see how many shots you can make into a garbage can. And then from that, you get percentages, right? You shoot 10, you make 7, you get 7 out of 10 or 70%. You could shoot a different amount to get working with fractions like 15, and you make 3 of them. Okay, so that's 3 out of 15 reduces down to 1 out of 5 or 20%. So there you got your fractions, your percentage, your decimals are in there, 20.2 when you divide the fractions, and you also have percentages. And a percentage, when you're dealing with these types of situations, are a probability. A probability is only between 0 and 100%. It can't go higher than 100% that something will happen. Like, for example, if you say, what's the probability it's going to rain today? It can't be any greater than 100% chance that it's going to rain. But could your money in your bank go up higher than 100% interest? Yeah, so percentages can be up higher than 100%, but probabilities can't be any higher than 100%. You can use decimals for percentages as well, or fractions for probabilities. They can't go less than 0. If it's not raining out, you say, what's the probability it's raining right now? And that'd be a 0%. So probabilities are always between 0 and 100%. So the game type of things, like I was saying, you could do with students to get them to learn about probability is, the probability that they make a shot. And that would be an experimental probability in terms of how you don't have a theoretical probability on that. You just have an experiment where they do over and over. Maybe each student in a group gets to shoot at that station. Then another group could play this slider football game where they slide this little triangle, if you ever played that in school, across the desk. And if it hangs over the edge, you get a point. Well, how many throws does it take you to get a what is called a touchdown when the point of the paper goes over the edge? And then from doing a group of people in a group trying that, you can get an average of the number of times that it would take. So there's an average. And plus you could talk about different types of averages then, whether you should be using your mean, median, or mode. Like, for example, if most people, it takes them, let's say, 10 tosses or flicks of that triangular piece of paper to hang over the edge, then but one person did it on one toss, then maybe the best average to use might be the median rather than the mean, because the one that got it in one little flick and got real lucky pulled the average down. So all these different types of games, and maybe you guys can think of other types of games your students could do to work with to calculate averages, percentages, and probability type of thing. And there'd be games that you could just make up for students, and they don't have to be games they play in class. You can show them real life data on baseball statistics. There's tons of baseball statistics, right? A batting average, when they say a batter bats 300, what they're talking about is 0.300, which is 3/10 really, or 30 hundredths or 300 thousandths. But either way, it's so far their average, their percentage of times that baseball player got a hit was 3 out of 10. If it's 0.3000, right? Well, or just 0.3 is the same thing. That is 3/10. It's saying that 3 out of 10 times this batter gets a hit. All sorts of stats in baseball. So maybe you guys can think of some of your own types of games or the use of statistics to do averages and also probability. So we'll have that on there as a question. So let's get into probability a little bit. And one thing that I think the easiest thing to get into with probability is just flipping a coin. And even though you're never going to have to do that in real life, it's easy enough that people can get into that and just have a penny around. Or what I have right here is a coin flipping program. So we get into these two words: theoretical probability. That's the actual probability of something happening. I think of that as being, that's what it should be. If you did it over and over and over and over again, you would see the results going to that value. An experimental probability is just what you get when you do the problem. Okay. Or even if a group of people did this experiment, flipping a coin, then there's a certain percentage of time that it lands heads, and it won't necessarily be the 50%. So the theoretical probability of a coin landing heads is 50%. There's two sides. They're not, it's not a weighted coin in any way. So since there's two sides and only one of those sides is heads, and it's just as likely as tails, then it's a 50% chance it lands heads, 50% chance it lands tails. It's as easy as that, 1 out of 2. But when you do this, if you do flip a coin over and over again, let's say 100 times, it's actually a very small probability that it's going to land heads exactly 50 times. But it should be around 50. And the more times that you do this, the closer it will get to 50%. So maybe you might do it 100 times, flip a coin 100 times, and it lands heads 48 times. Well, then my experimental probability would be 48%. So, and I'll do this problem in just a second, but I just wanted to read this little paragraph here. It says, it's good to have students run an experiment first to get an estimate of the theoretical probability. So this would be a good one with a coin flip, that you might want to just have them do the coins first and see what their experiment goes before you talk about, well, there's two sides and one side's ahead and all that sort of thing. Then students can also compare their experimental probability to their calculated theoretical probability to see if their theoretical answer could be wrong. For example, some students might think, well, what's the probability that you get one head on two coins when you flip two coins at the same time? Well, some people might think, well, that's a 50% chance. Maybe some people might think it's a 25% chance. Maybe that's the right answer. So they might get different answer by going through the probability. But if you have them flip two coins at the same time and see how many of those times, if you do this, let's say 100 times or 20 times or whatever, how many times that lands heads, you can see if what they think the theoretical answer is and their experimental answer, if they're very far off from each other. They should be close most times, right? Sometimes you get way far off on that. Like you can flip a coin and it lands heads, 6 times in a row or whatever. But if you do it over and over, your experimental answer should get close to your theoretical answer. So if they're not close, it either is just a rare circumstance or your theoretical answer could be wrong. However, we would expect the experimental probability to be slightly different from the theoretical probability due to the randomness of the experiment. If the experimental is greatly different from the theoretical probability, then that can happen, but it's likely that the reasoning of your theoretical probability is wrong. Like probably you didn't figure out the answer correctly. So let's get down to the coins problem here. So this is what we were doing here with the theoretical probability. A coin lands heads. That's 1 out of 2. And now let's go ahead and do this. Flip a coin 20 times and we'll count how many lands head and we'll get a probability on this. So this is something you might do with a student. So here's my coin flipping little app I found. And you might want to see if you could find a coin flipping program that would do more than flip just one coin, maybe one that would flip 2 coins or something like that. So here it is. I'm not going to count that because I just started the program. So I'm going to keep track of this. I'll flip this, so many times and just keep track of how many times it lands heads or tails here. So here we go. My first flip is tails. So I'll do it 10 times and see what I get here. Here's the second one, tails. Third one, tails. See 3 tails in a row. That can happen. Here's another one, heads. I'll do it 10 times, tails. So that's 5 times so far, and I've gotten 4 tails. Heads, tails, heads, heads, tails. So I just did this 10 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how many times did I get heads? Well, 1, 2, 3, 4, 4 out of 10 times. So therefore, my experimental probability is 4 out of 10, or 2/5, or also 4 out of 10 is the same as 40%, right? Divide and you get 40%. So my experimental probability is 40% of the time I get tails. So maybe a good thing to do is then compare that to the theoretical probability of 50% and compare those two and see, some people might say, well, this isn't a fair coin. It's landing tails more than it is heads. And that's why it's good to have a whole group of students. Now, another student would come up and flip the coin, or they could flip a real coin 10 times. Each student keeps track of it. So maybe mine might be 4 out of 10. Another student's might be 6 out of 10. Another student's might be 5 out of 10. And when you add that up from your 5 students, the average of those 5 students will even be closer to the 50% than what we have right now with the 40%. So that's a good layout for students to see how it goes. It would be also interesting to have a coin that isn't fair. It actually is programmed not to be random. Maybe it's programmed that tails shows up, 60% of the time and heads shows up 40% of the time. And then you can ask the students, does this seem like it's a fair coin, or is it biased, meaning it's going more towards heads or tails, like a weighted coin? There's such a thing as a weighted die that is going to land a certain way. A fair die is, and die is the singular of dice, but a fair die is where all 6 sides, if you're dealing with a 6-sided die, is that all 6 sides have the same probability of showing up. So that's the coin toss. I'll see if I can find one that tosses more than one coin, but, oh, there we go. Let's see. You can change the color of the coin. Flip number, flip again. And, well, I'd like to find one that maybe flips more than one coin. I'll see if I can find that. So a lot of information there about coin tosses. So let's go ahead and go back to the notes. And that's just an example, probably our easiest example of this. So here comes a harder problem that we can try. And this one, we're going to use the spinner app. And I'll show you that in a second. So let's keep track of this problem. So this one's a little harder. It's more towards, a teacher level here. So this one says a business has 3 job openings. You have 5 females and 4 males, 9 people total, that are applying for these 3 jobs. All are equally likely and equally qualified to get the job. Eugenia finds out that all 3 hired were male. That's kind of suspicious, isn't it? She wants to prove that the company was gender biased in their hiring. What is the theoretical probability that all 3 were male? Okay, so you get the idea here. We have, keeping track of this, we have 9 people total, and then you hire somebody. It's a random thing. Everybody is equally likely to be picked, just like a coin, heads, tails, because we're assuming that they did just as good. This is the assumption on this problem. They did just as good on the interview, and the resumes were just as good and everything like that. So why was it all 3 people hired were males? So before we do the theoretical problem, see, this is why this is how I'm going to do it. I think it's a good way is let's do an experiment with it. And this is something that you really have time to get into with students in elementary school. So let's check it out. So, and I think this could be done in maybe 4th grade or so. So put the names of, what we're going to do is put the names of 5 females and 4 males. And if you didn't have the app that I'm using, you could put it on, put these names on pieces of paper, and then place these papers in a box, shake them well, reach in and pull 3 names out. Mark down if all 3 were male or not. Repeat this experiment so many times, till you feel like you have a large enough sample that you can see how things are going, and your percentage would be close to the theoretical percentage. And so the question is how many of the times were all 3 male? So this would take a little while to do this experiment. And then what percentage of the 30 trials were all 3 males? Because I would think it'd be pretty unlikely. Well, let's get to the spinner program that I'm talking to you about here. And I think it's a good program. Let me make sure I can get this open. It takes a while for this to open. There we go, fine. Seems like I got to click on it 3 times for it to open. So here's my spinner program, and you have a link for this. Wheel of names. Well, you can put anything on this that you want, and let's make sure, and you can put in as many names as you want. So what we're going to do is follow what that problem said. And I think it said, let's keep track of it here. It said there are 5 females and 4 males. So let's make it really definite here what's going on. So Allie Beatrice, there's 2 females. Charles, let's see. I'm going to make these really easy to tell, or we could just say male 1, male 2 if you don't want to do that. So there's Eric. I'll tell you what, let's put in Brittany, because we have Brittany in the class, and let's do Eugenia, and let's do Gabi here. And let's see how many names we got here. I'll tell you what, I'll put my name in here. So how many was it again? It is 5 females. Okay. Let's see, 1, 2, 3, 4. I only have 4. 1, 2, 3, 4. Let's make this Erica. There we go. 1, 2, 3, 4, 5 females. And how many males do we have? Charles, Mark, and Mugabe. That's it. Charles, Mark, and Mugabe. So I guess we need 1 more male. So let's do 1 more. I have no idea. Let's do, I don't know. I don't know how to spell many names, so I'm just going to do that. My brother's name is Steve. So let's make sure we got 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 names. And 1, 2, 3, 4, 5 females, and 1, 2, 3, 4 males. So what we could do then is you just click to spin it. And what we're doing here is this spin is a simulation of them picking a person for a job. And we want to find the probability that all 3 picked are male. So we would do this, what we're going to do here, 30 times or so, and get a probability. So let's spin it and see what we got. Okay, there's the first one is male. So we're okay. And then we remove that name. Okay, so let's do it again here, because it landed on Mugabe, who's a male. So we're doing it again, and we need all 3 to land male. That didn't happen. So at this point, so I'll keep track of this. At this point, we've done this 2 times. Actually, it just was 1 time. It's 1 time of doing this process of seeing if all 3 are male. Well, that didn't happen this time. So I've tried it 1 time, and the answer is no, it didn't happen. We did not get all 3 to be males. So I'm not going to remove Erica's name. I'm just going to close it, and I'm going to put I think it was Mugabe who got removed from this, and I'm going to run the experiment again. Once the experiment fails on this, I'm done. It's just like flipping a coin. It's done quick. On this one, I have to spin it until I either get a female or I actually do get all 3 to be male. See, because that's what we're looking for, the probability that all 3 are male. So it did not happen on my first try. So let's try it again. And it didn't happen. I'm done. The reason is because we hit Brittany's name, and Brittany is a female. So that is not what we're looking for. What we're looking for is the probability that all 3 are male. That didn't happen. So 2 times so far I tried this, and neither time were all 3 males. Let's try it again. And you can make this easier and just do male, 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 like M, 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 and so on like that. Okay, so here's the first one. That's a male. So we're going to remove that. That person got the job. And we're going to spin again. So that was Charles. And we need all 3 to be male. No, did not happen. So I'm going to close it. See, I landed on Erica. So I'm going to go ahead and put, I forget who that was that got picked that time, but I'm just going to do, I'm just going to put male in here. So we still have our 9 names in there. So let's start again. So here's 3 times that we've gone through this, and we've not gotten 3 males in a row yet. So here's my first spin of this, my next try of this. And the first one is male. So I'll remove them and let's spin it again. And I get no. Hands on Brittany. See, so I've done it. I'll do it one more time. So let's close it and put, I'll just write male in again. So we got male, and where's male? See, so we could just do it like that instead of doing names, however you would like to do it. So this is my 5th try to get 3 males in a row. No, didn't happen, Erica. So 5 times, no, it did not happen. So right now, we could be thinking, geez, this is a pretty rare event, right? To get 3 males in a row, even though we have 1, 2, 3, 4. I think we have 5 males in here. Let's see. 1, 2, 3, 4. Geez. Oh, I think, let me see. I hope I have this set up right. Let's make sure we have, how many males were we supposed to have? Only 4 males. Yeah. And geez, they got 3 of the people, right? 3 job openings. All 3 were male, and there was only 4 males applying, 5 females. Pretty unlikely that this is going to happen, right? So we've done this several times, and I don't know how many times we might have to do this until we finally get, 3 males to be picked. We'll try one more time. Pretty unlikely. It's trying to like win the lottery here on this. So done again. So done. Beatrice, that's a female. So I've done this now, I think 7 times, and I have not gotten 3 males in a row yet. So that's 7 times. So that's no, 7's no. I tell you what, it's pretty easy to do, because once you get a female, it doesn't happen. Let's go 10 times. 8, 9, 10. See if we get it. Brittany. Nope, Brittany's female. So that's 8 times that it didn't happen. I don't have to put the names back on because none were removed. Okay, so there's 1. Okay, there's 1. Let's remove, and I'm just removing that 1 male. So that's 1. I need 2 more males now to be picked. Here we go. No. Okay, so that's 9 tries on this. And let me put the male name back in. I'll just say male 2. So there's 9 names back in. That's 9 tries. I tell you what, we've only gotten a male. Just only a couple times did we get 1, let alone 3. Okay, we're done again, right? Beatrice. So that's 10 times. No. Now something tells me then that the probability of this happening, the theoretical probability that this is going to happen, is really, really low. So, because that's 10 times and it didn't happen once. So let's actually figure this out. So probably this was too rare of an event for students to do. Maybe I should have done something like, what's the probability that 2 males are selected? That one we might have gotten. I don't think we did get that here, but we might have eventually got it. So let's go here and work out the theoretical probability. I think that's right here. So the way you do this is, let's keep track of it. We got here, I'll just write it in here. So we have 5 females and 4 males, and we want to keep track of the total. So the total is 9 people, right? And what we're looking for is the probability that all 3 people that get the job are male. So I'll just say probability, the P stands for probability of male, 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 male. So the probability that the first one is male is what? Well, there's 4 males out of the 9 people total. So that's 4 out of 9. Now, that person was removed just like we did on the spinner game. And that's why the spinner game is so nice, because you can see what's going on. Now that that person's gone, that male is gone, man, that hurts your probability, because the number of males now drops to 3 and the number of people did drop to 8. But 4 out of 9 is a higher probability than this one. So now, getting this, the second male, 3 out of 8, pretty unlikely. But then after that, the probability that the next one is male, when 2 males have been removed, there's only 2 males left, but there's 7 people still in there. Okay. So now to get the answer, we need to multiply these fractions together. And you can do that if you wanted to work with students on this. First of all, you could do it where you multiply straight across and get it. But another thing you can do is reduce the fractions. So this is the good work with fractions that you might do. Like, for example, you can cross off like the 4, or divide out is the proper way to say that. The 4 goes into 4 1 times and 4 goes into 8 2 times. So there's lots of ways of dealing with these fractions. One thing you can see is 4 times 2 is 8, and we have an 8 in the denominator. So basically what we're saying is we have 8 over 8, which is 1. And so we can cancel that out because this is 1 times the remaining fraction that's there. Plus the 3 over 9 reduces down to 1/3. Now at this point, you might say, well, what number do I have on the top? I've had students do that. You don't have any number on top. It's a 0. No, you have a number on the top. The number that you have on the top, let me move this over here a little bit. The number on the top is a 1, because remember, these did more than just divide out. What they did was they divided to 1. So when you did this, 4 times 2 is 8, and here's an 8, really, it just divided these to 1. Like, for example, this is 1/3. 3 over 9 is 1/3. And 2 times 4 is 8, but 8 over 8 is 1 over 1, same as 1 over 1. So now on the top, the numerator, we just have 1, multiply cross. 1 times 1 times 1 is 1. And on the bottom, 3 times 1 times 7 is 21. Now, the nice thing with this being a 1 up the top is that you can say, here's my theoretical probability. This is the actual probability of this happening. It's a 1 out of 21. 1 out of 21. Only 1 out of 21 times should all 3 people that are randomly picked for this job that Eugenia applied for, should all 3 of them be male. 1 out of 21 times. Well, there's a thing in statistics that is called an alpha level. And we did not get to this in any class, but it means that if the chances of this happening by randomness is below generally 5% chance. So if this fraction here is less than a 5% chance of happening, then it's so unlikely that actually Eugenia would have a case here if she took this situation to court. So let's check it. It's just a little bit of arithmetic here to take 1 divided by 21. So if I do 1 divided by 21, I get 0.047. See, 1 out of 20 is 5%. 1 out of 21 is even smaller because the denominator is bigger. See, with the denominator being 21, not 20, that makes the whole fraction smaller. So I get 0.476, which as a percentage is 4.76. Since 4.76 is less than, and let me just give myself a little bit of room here, since 4.7%, 4.76% is less than 5%, then we would say that this company does have a hiring bias with them, that's going on. And then you could, if you wanted to pursue something, you could. There are companies out there that do that. There's lots of data out there about women being paid less than men for doing the same job, same experience. And there's also just in general, there are companies that don't want to hire women. So, she might have a case here against this company. So that's the theoretical probability. And as a fractions, it's 1 out of 21. So basically, if I would have played this game 21 times, and what this says is if I play this game 21 times, I should have the 3 males come up 1 time. That's the expected number of times I'd have to play the game, 21 times. Well, I did it 10 times and it did not happen. I'll tell you what, let's do the game. So probably this is so rare of an event. In terms of a case for gender bias, this has it. So this is a good example of gender bias. And some people might say, well, geez, it's just luck. Well, it's random. Very low probability that this would happen by randomness. Let's say we're the same thing. We're just looking for 2 males. This might be a better problem. 2 males. And on this, with the same number of people, that would be the probability that the first one is male is 4 out of 9. And the probability that the second is male is 3 out of 8. See, it's just the first 2 fractions that we had. Now, if you reduce this down, see, and these are easy to reduce. 4 goes into 8 2 times, 3 goes into 3 1 time, and 3 goes into 9 3 times. If I could take this across, I get what? 1 out of 6. So therefore, if I would play the game, and this doesn't say this is a theoretical probability, 1 out of 6. So 1 out of 6 times I should get 2 males, right? Male and male. Would she have a case if it was just 2 males? No, because 1 out of 6 is 0.16 repeating. The 6 is repeating, which is the same as a 16.6%. That's not, I'll say this, it's not less than the 5% chance that's used for these theoretical, to prove a case of gender bias type of thing. So 16.6% is not less than 5%. So we cannot say that it would be gender bias if they only hired 2 males, even though it was just 2 people hired and both were male. Can't say gender bias. 3 males, yep, it's less than a 5% chance, and that's down to that low probability of that happening by just coincidence. So they're playing a game. Here is the most likely situation. Okay, so I tell you what, I think that's a pretty good problem there, and you could do all sorts of things with this to make it easier. You could use your students' names in your class. That's nice. Or if you just want to make it easy, let's do the same problem, and we'll just try for 2 males this time. So I'll do male 1, and then I'll mix them up, female 1, male 2, and it really doesn't matter the order. Some people might say, well, let's put would do every other like this. It doesn't matter. It's still the same amount of space. That's a good question for your students as well. Let's put a few females in here. Female 3, you can say to your students, put them in any order that you want. Female 4, female 5. Remember, there is 5 females and only 4 males. So there are male 1, 2, 3, and 4, females 1, 2, 3, 4, and 5. We'll play this 6 times because we just figured out the theoretical probability is 1 out of 6 times I should be able to get 2 males in a row. First 2 being hired, there's only 2 being hired, so I get a male and get a male. Chances of that happening is 1 out of 6, which means flip that 6 times I have to do this for me to expect to get 1 male. Now, that's a theoretical thing. It may happen the first time. It could happen the 7th times, could happen the 10th, the 12th, could happen the 2nd, all over the place. But I would expect to get a male. The most likely outcome is I get a male on the 6th time. I don't think that that's going to happen because each one of those has a probability. The probability that I get two males on my sixth try, that's the highest probability. But all of them have a certain probability. So it should be around the sixth try. This is, again, something you do with students in groups, and you have them all try this. That way, if somebody is a fluke situation and they get the two males on their first try, and the other one took 12 tries, when you do the average of the number of tries, it evens out. So let's give it a shot here. So here we're checking for two males in a row. So let's check it. And it did not happen. So this is a big no. See, I don't need to go any farther. Don't need to remove the name or anything like that. So let's go again. That's my first try. I did not get two males in a row because my first one was a female. So that's number one trial. No, did not happen. So here's my second trial. No. That's two no's. Okay, let's try it again. So this is my third trial here on this. Wow. Three, the big no. Let's try it again. Okay, so in my fourth try, I haven't done it yet, but my first try, I did get a male. But remember, I need two males for this to be a success here. So let's remove the name. That person got hired. Okay, so now we're down to 8 people. When I do this experiment again, I'm gonna have to put that male name back on it. It was male 3 that got picked. So here we go. Do I get a winner this time? See, for me to be a winner, I need the first 2 to be male. It happened. How many tries did it take? I got male 3 and I got male. So let's remove him, but it's done. It happened. And that was male, what was it? 2, male 2. So male 3 and male 2, done. How many tries did it take before I got 2 males in a row? 4 tries. But we know that on average, it would take 6 tries. How do we get the 6 tries? We got that probability of 1/6, and then we just flipped it. Okay. So, and if you're having a hard time understanding why you flip it, let me go back to the notes here 1 second. So think about it this way. On a coin, it's a, and this is something you could do, make this problem even easier. On a coin, it's a 1/2 of the time, the theoretical probability of getting ahead is 50%. So half of the time you should get ahead, right? Theoretically. So how many would you expect? This is what we're talking about. How many would you expect? How many times would you expect to have to flip a coin to get ahead? Well, just flip that number, flip the 1/2, invert it. You get 2. It would take 2 flips. Now, the reason why that is because you just take the number of flips times the probability. And so if you do the number of flips times the probability, how many are we looking for? We're looking for this to happen once, that we get 1 head. Well, the n is our unknown, the number of flips. The probability of getting ahead is 1/6. So some number times 1/6 is equal to 1. Well, what number times 1/6 is equal to 1? It's reciprocal, right? 6/1. 6 times 1/6 is equal to 1. Same way with the coin. With the coin, how many flips, the number of flips, times the probability of a coin landing heads is what? 1/2. N times 1/2 equals 1. What number times 1/2 equals 1? 2, right? You could solve it this way. You could say this is n/2 equals 1. How do you solve that? Well, you can just cross multiply right there. Multiply this side by 2, multiply this side by 2, and you get n equals 2. So we would expect that it would take 2 flips to get ahead. So you know what? I got that coin toss here. Let's do it, run a little experiment on this one. The theoretical probability for the number of flips that it would take to get ahead is 2 flips. So let's do it. We'll keep track of it. Here's flip number 1. I got tails. So no, it didn't happen. Here's the second try. I got heads. So that's just luck that that happened perfect like that. But it took 2 tries to get ahead. But again, this is an experimental thing. So you run your experiment over and over again. So this took exactly 2 tries. Let's try it again. New count here. First flip, heads. I got it on my first try. Now you would do this over and over again, and then you could get an average of the number of times that you would need to do this. So far I got heads on 2 flips. Then the next try through, I got heads on 1 flip. And then here's my third try, tails, heads. Again, 2 flips. 2 flips to get ahead, then it was 1 flip to get ahead, then it was 2 flips to get ahead. On average, if you do this enough, you'll see that average get closer and closer to 2 flips to get ahead. And again, the reason why it's 2 is because what we just looked at here. The probability is 1/2. And we say, what times 1/2 gives me 1? 1 success is what that 1 stands for. Well, the inverse of that. Okay, so we're going to do another one like this. So this one is on rolling a die. Now, I got several dice programs here, and you might have to see which ones you might need for a certain homework problem, because maybe it wouldn't be a regular die. Like a normal die is a cube that has 6 sides, right? But there are other dice that have maybe 12 sides or whatever. So depending on the homework problem, you might want to use a different simulation. There's also problems with dice where instead of rolling 1 die, you're rolling 2 dice, and you're seeing what the sum of those dice are. For 2 dice, the most likely number that comes up of the 2 dice is 7. There's 6 ways to get 7. 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. There's 6 ways. But to get the sum of the dice to be 2, there's only 1 way. 1, 1. That's the only way. So that's why 7 is most likely. For example, 11, there's 2 ways. 6, 5, or 5, 6. So, you could have different sides, different number of dice rolled, all sorts of things you can do with these simulations. So here's the question. It says, on average, how many times do you have, this is a good problem here. On average, how many times do you have to roll a 6-sided die until all 6 numbers show up? Okay, so what I'm doing here, I'm going to roll a die, and then I'm going to see what number it is. Then I'm going to do it again, and I'm going to keep account of how many rolls it takes until all 6 numbers of a 6-sided die show up. That's a pretty hard thing to figure out the theoretical probability for. So again, I'm going to do the experimental one first, and this would be so that students could get an idea of like how many what it really is, what the real answer is. And it should be, you would think, close to the experimental one. So let's go ahead and do and we'll see which one of these is the best one. Really, we just need a single die to be rolled. Now this one's okay. With this one, I can pick the number of dice. Like see here, number of dice, there's 2 dice, but I could increase it or I can decrease it. For this problem that we're doing, it's just 1 die being rolled. And then you can also pick the number of sides on the dice and the number of dice here. So wow, that's pretty interesting. So all those are possibilities, and they give you dice shapes and stuff like that. In fact, I kind of would like to see what the 8-sided die looks like. Let's see. Oh, okay. It doesn't really show you the die on that. Oh, and then you click stop, and there's an 2 8-sided die. Heck, didn't see down here is what they really look like, these weird looking dice. Now, I think the other one looks nicer. I'd really like to see the die be rolled and go across the screen, or a coin that looks like a coin when it's being flipped and things like that. This one, I think the other one might look nicer. Let's take a look at the other one. So let's look at this one. It's not too bad, the last one, when it was just a 6-sided die. So this one, I like the way it spins. It just looks more real. I wish it was going across the screen or something like that. And then you are able to change your number of sides here, but you're not able to change the number of dice being rolled. So that's fine with us because we're only going to do one die. And what we're doing with this problem again is keeping track of how many rolls it takes until all numbers show up: 1, 2, 3, 4, 5, and 6. So let's keep track of it. Here we go. So I'm going to start. So my first one I get is a 2. Well, that's great. And that's my first roll. Now I'm looking for a different number. Now, see, the probability that this first one was a number that hadn't come up yet is 100% because I hadn't rolled yet. So the number 2, boom, I'm done with that. Here's my second roll. And I got a 6. So we're just going to keep going here. And that's a winner. So we got 2 different numbers. We're going to say, how many times do I have to do this until all 6 numbers show up? Here we go again. My third roll is a 2. Guess what? That didn't help me at all. I need, what I still have left to get is a 1, 3, 4, and 5. So here's my fourth roll. It's a 1. Yay. So at this point, I have the 1, 2, and 6. Next roll, a 3.